Part 3 of Foundations. How foundations are actually built. Step-by-step construction, materials, and the details that determine everything. Most people think building a foundation means digging a hole and pouring concrete. And I understand why. That is what it looks like from the outside. You drive past a construction site, you see an excavator digging, you see a concrete truck pull up, and a few days later there is a slab on the ground. But what happens between that first cut of the excavator and the moment the concrete truck leaves? That sequence, those materials, those decisions, that is where everything is won or lost. A foundation built with the wrong concrete specification, with rebar in the wrong position, without proper moisture protection, without being cured correctly, that foundation looks identical to a well-built one from the outside. 4 or 5 years, maybe 10. And then it begins to tell the story of every shortcut that was taken. In Part 3, we go through the real process. Every step, every material, every standard that separates a foundation that outlasts its owner from one that becomes a liability. Before we go further, if you are actively building a home or planning to break ground this year, drop a comment below with your country and the type of soil on your land. I read every comment and I want to help you figure out the right foundation for your exact situation. And make sure you are subscribed because Part 4 is going to be the most valuable part of this entire series. We expose every major foundation mistake, including the ones that are so normalized on job sites around the world that most people do not even know they are mistakes until the damage shows up years later. Segment 1. Pre-construction. The documents you need before ground breaks. Before one shovel of earth is moved, 3 documents must exist on a well-run construction project. The first is the geotechnical report, the soil investigation we discussed in Parts 1 and 2. It must be prepared by a qualified geotechnical engineer who has physically tested the soil at the depth required for your foundation. This report tells the structural engineer what they are designing for. Without it, foundation design is guesswork. The second document is the structural engineer's foundation drawings, dimensioned, detailed drawings that show the exact size of every footing, the depth of every foundation element, the size and spacing of every piece of reinforcing steel, the concrete specification required, and the connection details between the foundation and the structure above. In many countries, these drawings must be approved by a regulatory authority before construction begins. In countries where this approval process is weak or optional, the temptation is to skip the structural engineer and build from habit or from a neighbor's plan. This is one of the most common and most dangerous practices in residential construction globally. The third document is the construction specification, a written document that accompanies the drawings and specifies the material standards, testing requirements, and quality control procedures that govern the work. Together, these 3 documents define exactly what needs to be built and to what standard. Everything else is execution. Segment 2. Building a slab-on-grade foundation, complete step-by-step. Step 1. Site clearing and stripping. The entire building footprint and a working margin beyond it must be cleared of all vegetation, roots, and topsoil. Do not underestimate this step. Topsoil is organic material. It is biologically active, it contains roots and plant matter, and it is compressible. You cannot build on topsoil and expect stability. Topsoil stripping depth is typically 150 to 300 millimeters, 6 to 12 inches. But this varies depending on how deep the organic layer goes on your specific site. On a site that has been previously farmed or where vegetation has been established for many years, the organic layer may be deeper. All stripped topsoil must be removed from the building footprint. Stockpile it elsewhere on site if you want to use it for landscaping later, but it has no place under your foundation. Step 2. Excavation and subgrade preparation. Once topsoil is stripped, the subgrade, the natural soil below, is excavated to the formation level required by the structural drawings. For a slab-on-grade, this is typically 200 to 350 millimeters below the intended finished floor level to allow for the subbase, the vapor barrier, and the slab thickness. The excavated subgrade must then be proof-rolled. A loaded vehicle is driven over the entire area to identify any soft spots where the subgrade deflects under load. Any soft or yielding areas are excavated deeper and replaced with properly compacted granular fill. This proof rolling step is routinely skipped on residential projects, and it is one of the reasons slabs develop localized cracking and settlement in specific areas. Step 3. Compacted granular subbase. A minimum 100 mm 4-inch layer of clean crushed stone or well-graded granular material is spread across the entire slab footprint and mechanically compacted in layers using a plate compactor or vibratory roller. The subbase performs 3 critical functions. It provides a uniform, stable working platform for all subsequent operations. It improves drainage beneath the slab, directing water away from the base of the concrete, and it interrupts the capillary rise of moisture from the soil below, the natural tendency of water to wick upward through fine soil particles toward the underside of the slab. Compaction must be verified to a minimum 95% standard Proctor density, not estimated visually but tested by a materials laboratory. Step 4. Vapor barrier. Over the compacted subbase, a continuous polyethylene vapor barrier is laid. Minimum 0.15 mm thickness, which is 6 mm in imperial measurement. For premium protection, 0.25 mm or 10 mm is specified, and in areas with high water table pressure or below slab moisture issues, a reinforced vapor barrier or a dedicated sub-slab drainage system is warranted. The vapor barrier must cover the entire slab area with sheets overlapping at all seams by a minimum of 300 mm, 12 inches, and all seams and penetrations must be sealed with compatible tape. The barrier is turned up at the perimeter and lapped over the edge formwork. Tears in the barrier during subsequent operations must be immediately repaired. This membrane is the last line of defense against moisture entering the slab from below, and the consequences of a poorly installed vapor barrier, damp concrete, flooring adhesive failures, mold under vinyl and carpet, efflorescence on the slab surface, appear months and years after construction, often after the builder has long since left the site. Step 5. Formwork and edge beams. Timber or steel formwork is set around the perimeter of the slab to contain the concrete during placement. For a residential slab-on-grade with turned-down edge beams, sometimes called a thickened edge slab or monolithic slab, the perimeter beam is typically 300 to 450 mm deep and 200 to 300 mm wide. This beam carries the concentrated loads from the wall above it and provides stiffness to the slab perimeter. The formwork must be set accurately to line and level. The finished concrete surface will directly reflect the accuracy of the formwork. Any deviation in the formwork translates into a deviation in the slab. Step 6. Reinforcement placement. Reinforcing steel is placed in accordance with the structural drawings, typically deformed bars at specified spacing in both directions across the slab body, with additional reinforcement in the edge beams and at re-entrant corners, which are internal corners in the slab plan that are concentration points for cracking. All steel must be supported at the correct height above the vapor barrier using plastic bar chairs. Small plastic supports that hold the bars at the specified cover distance from the bottom of the slab, typically 50 to 75 mm. Steel laps, where one bar ends and the next begins, must meet the minimum lap length specified in the drawings, typically 40 to 60 times the bar diameter. All these details matter because concrete without correctly positioned steel is not reinforced concrete. It is plain concrete with steel somewhere inside it. Step 7. Plumbing and electrical rough-in. Every pipe, conduit, and sleeve that must pass through or be embedded in the slab must be installed before concrete is placed. Drain lines, fresh water supply pipes in regions where they are run below slab, electrical conduit for sub-slab power and data. All of it goes in at this stage, is positioned correctly, is supported so it cannot move during concrete placement, and is pressure tested where applicable before the pour. This is a permanent, irreversible step. Once concrete covers these systems, any mistake requires saw cutting the slab, excavating, repairing, and repouring, a process that costs several $1,000s at minimum and disrupts the entire construction schedule. Step 8. Concrete placement. Concrete is ordered from a ready-mix plant to specification. For residential slabs, a minimum compressive strength of 25 megapascals, approximately 3,600 psi, at 28 days is standard in most codes, with a maximum water-to-cement ratio of 0.50. Concrete is placed by chute directly from the truck or by concrete pump for larger pours or restricted access. As each section is placed, a vibrator, an internal vibrating probe, is inserted at regular intervals to consolidate the concrete, eliminate air voids, and ensure it fills all spaces around the reinforcing bars. A screed is then used to strike the surface level with the top of the formwork. This is followed immediately by a bull float, a large flat tool pushed across the surface to embed aggregate and bring cream to the surface. As the concrete begins to stiffen, a power trowel produces the final finish. Step 9. Control joints and curing. Concrete shrinks as it cures, typically around 0.04 to 0.08% of its length, which in a 10-meter slab is 4 to 8 millimeters. This shrinkage causes tensile stress in the concrete, and when that stress exceeds the concrete's tensile strength, it cracks. Control joints, saw cuts made into the surface of the slab to a depth of 1/4 of the slab thickness, create planned weak lines where the concrete cracks in a controlled, straight manner rather than cracking randomly across the surface. Control joints should be placed at maximum 3 to 4 meter intervals in each direction, and always at doorways, changes in slab thickness, and column locations. Immediately after finishing, curing begins. Concrete cures, not dries, through a chemical reaction called hydration between the cement and water. For full strength development, this reaction must be sustained by keeping the concrete moist and at adequate temperature for a minimum of 7 days. Curing compound, a liquid applied by sprayer that forms a film on the surface to retain moisture, is the most common method on residential sites. Alternatively, the slab can be covered with wet burlap hessian and then plastic sheeting to retain moisture. Skipping or shortcutting curing is one of the single most costly mistakes made in concrete construction worldwide, and we will come back to it in full detail in Part 4. Segment 3. Critical Materials and Specifications Summary. Concrete grade and mix design. For residential slab-on-grade, minimum 25 MPa, 3,600 psi. At 28 days, water-to-cement ratio not exceeding 0.50, maximum aggregate size 20 millimeters. For basement walls and footings in cold climates or sulfate-bearing soils, minimum 32 MPa, 4,600 psi, with sulfate-resisting cement and air entrainment for freeze-thaw durability. For pile caps and mat foundations carrying heavy loads, 32 to 40 MPa. Always order from a reputable ready-mix plant with documented quality control. Never batch concrete by hand for structural elements. Reinforcing steel. Grade 60 deformed rebar, yield strength 420 megapascals, is the standard for residential foundations globally. In coastal environments or areas with high chloride exposure, specify epoxy-coated rebar at a 20 to 30% cost premium over standard bar. In highly corrosive industrial environments, stainless steel rebar may be specified. The bar must be cleaned, free of loose rust, mud, oil, or paint, at the time of concrete placement, as these contaminants reduce the bond between steel and concrete. Waterproofing systems. For below-grade walls, a spray-applied polyurethane or bituminous membrane on the exterior face, combined with a drainage composite board, geotextile filter fabric, and a perforated drain pipe at footing level discharging to a sump or gravity outlet. This complete below-grade waterproofing and drainage system adds $3,000 to $8,000 to a standard residential basement, but eliminates the most common cause of basement moisture problems. For slabs, the vapor barrier system described above, combined with proper perimeter drainage and site grading. You now know what every major foundation type is, where it is used, what soil conditions it addresses, and how it is built from start to finish. But here is the hard truth. All of that knowledge can still be undone by mistakes. And Part 4 is going to be the most important part of this entire series. Because we are not just going to talk about the obvious mistakes. We are going to talk about the ones that nobody warns you about. The ones happening on sites right now, today, all over the world, by builders who genuinely do not know they are doing something wrong. These are the mistakes that do not show up for 5 or 10 years, and by then, they are somebody else's problem. Unless you are the homeowner, do not miss Part 4.